Okay, I guess we should get started, but let me just mention to the people that just came in, may not have heard. We started engaging interest in a reinforcement learning study group that would start after the study group ends. So the first meeting would be April 11th. And in that post, I asked for 30 people. I said if we could get 30 people, that would be enough to start the class. And we ended up getting almost 50 people. So yeah, so that looks like it's going to go. And the first meeting will be April 11th, and it'll be this time slot, 10 o'clock on Sunday. So yeah, I'm excited about that. So I guess, Mayank, you can go ahead and start because I think maybe this is all we get today.
Yep. So let start. Full difference learning I've posted in Slack, and let's try to complete the through dueling DQing. And I will share a timer.
What time shall we reconvene?
I think so 50 minutes will be more than enough.
50 minutes? So that's, yeah, so that's 11 o'clock, roughly?
Yes. Yeah.
Okay.
So I'm starting the timer. Let's begin. Hey guys, let's take 10 more minutes here. Uh, since I had some problems running the code.
Yeah, can you repeat that? I'm sorry, I missed part of it.
Yeah, can we take 10 more minutes here? I had some uh, difficulties in running the code, and I needed to. Yeah, let's reconvene after 10 more minutes.
So I actually put in, and I don't know if I missed the last call, unfortunately, but I had put in an issue that I had had. Are you having the same issue in the code, or is it
Mm,
different?
no.
Yeah, I let's see, I
You
found the same
submitted a
issue.
question, yeah, yeah.
I did, and I found that fortunately I was able to execute the thing on my own machine. Rather, it didn't work in Colab, but I was able to execute it on my own machine.
I guess I see. Okay.
Yeah.
Yeah, I was just wondering if he was having the same problem because he may not be able to solve it if it's in Colab. Okay, but I'll give it a try on my own machine.
Now, is it solved right now, or do you still need help with
N-
that?
Not in Colab yet, but
Okay.
I think Joseph just said if you run it on your own environment, it will
Mhm.
probably run.
Yeah, but if I think you need a GPU to make it run
Oh, so that's not
in
gonna work
in
for me.
in finite time. Yeah,
Yeah,
yeah. Mine has a GPU, so it was able to run on it.
yeah, it definitely makes a difference if it's GPU or not. And Maya, you can look in um, what is it in Slack, and I think I put the actual error message and see if yours is the same. I know Joseph said he submitted a ticket on it as well, or questions about it, but nothing's
No,
come back from that yet.
I am going through the. Uh, my code is running fine. I'm going through the various formulations of the prioritize and double DQNs. So I need
Are
a
you
bit of
on? Are
time.
you running it? Are you running it in Colab?
No, no, I ran it on my personal machine.
Yeah, yeah. It runs fine on a personal machine. It's the problem is with the Terrence found was in Colab. Yeah.
I hope you can see my shared screen.
Yes, we can.
Uh, let's now begin with the Q-learning part. First, we have to go through TD. So, what TD was, temporal difference learning is a class of algorithms, which is very much similar to the value equations. Um, but what's uh, uh, it's based on the Markovian uh, chain modeling. So last time we discussed about what Markov chains are. Let me get the diagram here. Yeah, and what the transition probabilities are in a Markov chain, and how do we use that partial knowledge of a MDP to reiterate, and what is the kind of a exploration policy that it uses. So uh, we discussed this in the last uh, uh, call. Now we are taking it forward by introducing this TD learning algorithm. This is the vanilla one. Uh, then there are extensions to it with respect to the TD lambda approaches and by Sutton. We will we will just take a look at this. Uh, vanilla one, and uh, since what it, as I alluded to earlier, what it does is uh, the experience state of those transitions must at least know the rewards. These kind of plus 40, plus 10, minus 50, these are the rewards. And we model that on MDP with respect to this guy here. Yeah, these are the transition probabilities that we modeled it, that we have seen last time. So we kind of assume here that this model only has a partial knowledge. So here, firstly, will we calculate the using the dynamic programming approach, in which we iterated through all the state action value pairs, and next and got uh, our optimal policy with respect to this Q value iteration here, the last time around. Now we are going through the TD approach, in which the TD target and the error, uh, which is only based on the partial knowledge of a MDP. Here, this will explore based on that random policy that it has to take, and those transitions and rewards of those state action value pairs will be governed by this equation here. So uh, B here bk plus 1 of s can be written as a 1 minus alpha vk, that's the value of that state s multiplied by the alpha into reward plus the gamma, that's a discount factor of the value of the next state, where, or it can be equivalently broken down to this, uh, and this guy here is called a TD target, and this guy here is called a TD error, and we just kind of use this uh, to get our approximate kind of uh, solution to the problem that we are trying to solve. So that will result in the reduced variance as uh, opposed to the SARSA and other approaches. Uh, I'm going down to the literature, uh, the throat and the theoretical intuition behind that. So that's how it works. And then this is a way of writing these two sets of equation in a concise form. So and this is a practical tip that TD learning has similarities with the stochastic gradient descent, and it handles one sample at a time. Uh, uh, and it's like stochastic gradient descent. It can truly converge if you gradually reduce the learning rate. Otherwise, it will just keep bouncing around the optimal Q values. Maybe you guys have seen those graphs in which the stochastic gradient descent variant always bounces across those optimal uh, inner circles, and uh, it's never truly able to converge, and it just uh, has those variations that mm, uh, makes it impossible to hit the sweet spot. So then for each state S, this is a class of that, and then we go on to Q learning. Here, Q learning is an adaptation of the Q value iteration, and where the transition for probabilities are and the rewards are initially unknown. And what we do here is we gradually improve the estimates of the Q value, and this is accurately reflected in a Q value estimates with respect to the optimal policy that's being chosen with respect to the max operator that is being applied here. So it will result in a greedy policy. It might not be optimal, but yeah, it will have those uh, greedy approaches, and we will see how much time it will take to converge versus the optimal Q value pairs. Then we take a look at the algorithm of at how the step and the exploration policies are defined. So this is the vanilla and the simplest possible way to define the step and the exploration here. And there are many variants and additions to do it that we will see later. So uh, this is the probabilities that we select, the next state based on a random choice, the rewards that it has, and it returns this. Uh, this is the simply exploration policy here. Then we have those alpha, decay, gamma, and state values, which are the uh, hyperparameters, and then those based on those hyperparameters, we pass in the state, which gets the iteration, which gets the action. Sorry, yeah. The next is the step, then the max. With this is all in regards to the equation that we saw here. 18.4. If we take this and look at the code here, yeah, yeah, we can see it here, how this is formulated. So with the greedy policy are the next step that we take, then the alpha values based on that particular alpha value, we get that decay. And this is the equation that we use to apply to get to that next state. And this after the 10,008 iterations, we get this Q values. Mm. This is based on this approach. And when we run this, the algorithm will converge to the optimal Q value here. If we see on the Q learning part here that we just ran, and this will take initially, if you can see, this only takes approximately 15 iterations to reach convergence for the Q value iteration. But for the Q learning, it takes around 8,000 iterations to converge. So, uh, since we do not know the transition probabilities of the rewards, so it makes it significantly harder to converge here. That's the whole reason data of why Q learning was introduced. And this was introduced by Watkins in 1989, and they had a paper in 1992 which expanded on this. And it's a very good read, and I will recommend you guys to go through it. This is the Watkins and Peter Dan Q Learning 1992 paper, and it's a kind of model free. So yeah, and they have expanded on many things. So with respect to those Markovian environments, ACE, synchronous dynamic programming, the ARPs, the action replay processes. This was paper. So this was about Q learning. Any queries? So next, now go forward to the exploration policies of how we explore, since we just looked at the max function there, but there are uh, many better options with respect to the epsilon greedy or exploration that we can take at each step. So it at each step, what epsilon greedy does, it acts randomly with the probability of epsilon that we give, and there is or greedily with this probability 1 minus epsilon. The advantage here is I've highlighted it here, that it will spend more and more time exploring the interesting parts of the environment as the Q value estimates get better and better, while spending some time visiting unknown regions of the MDP. So this will reduce this. You can intuitively think of like the exploration versus exploitation problem. And those parameters between 0 and 1 will how you choose those parameters will uh, move your turn your knob towards uh, how much uh, 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 rewards that you want to explore, in the sense that it will go towards the un uh, visited states more, and then there will be that uh, it will of course take more time, but you can find a path that is optimal there. That's close to the optimal. But the trade-offs are there. They will have to choose depending upon uh, what you want to do uh, based on the particular situation or the environment that you are in. And then yeah, this is the formulation for that. So this is, as I alluded to earlier, this was based on the exploration function, and you can also reduce, you can also think of it as a kind of a curiosity parameter, where you can have this curiosity measure, uh, q plus k by 1 plus n, and how the agent is attracted to the unknowns. That will define this. Then we can use this parameter here too. But this is not being implemented here. We can, of course, implement our own to see the explorations with respect to the mm, curiosity hyperparameters that are being added. So maybe that's a task for us. This is with respect to exploration. So any queries here? Okay. Now moving forward. Now, how can we approximate the Q learning and the deep Q learning here? Um, Here, it gives that the scaling is not well to a large or even medium MDPs. And if the number of states are greater than this guy here, this is a Pac-Man agent that they are using to train, then the number of atoms, so the states, the number of possible states become larger than the number of atoms in a planet. So you can never actually keep a track of the estimate or every single Q value. And then they have given a solution as to find the approximations of those, the state action pair, using a set of manageable parameter vectors. Here they are known as theta. Then yeah, they have given a difference between how classically they used to have a sort of a linear combination of handcrafted features, and now they use a estimator of Q values, which I think so they introduced in 2013, DeepMind, for their DQN. Yeah. Uh, this is the paper that they introduced in playing Atari with a deep reinforcement learning. So here they introduce a variation of to estimate the Q values using the function approximations. And then how do we do that? So this is a Q learning with an pseudocode for a deep Q learning with the experience replay. And they firstly, if I go to the algorithm briefly, how they do it is they initialize the replay memory. We will take a look at the replay buffers and those prioritized buffers and data in the chapter. But yeah, uh, those you can think of it is that is I think so implemented as a doubly linked list here. But yeah, we can also understand it in the form of tricks or kind of uh, uh, how do I say it? The advancements that were made in this field to come up with those optimal uh, uh, the optimal way to run those algorithms on the severely limited compute that we currently have. Maybe if in the future we have quantum chips, then it will be much more easier. But yeah, right now those compute limitations give us the reason to approximate Q value learnings, uh, those approximations that are necessary. Yeah. So let's now move forward. This is a kind of a Huber laws that they use while training it. If we look at the code, this is from a theoretical perspective, but if we look at the code, uh, do we approximate it? Yeah, this is with respect to those implementations factors here, just given the epsilon greedy policy. It's been taken. Here we give the app by default we choose it 0, but in the epsilon that sorry in the algorithm that we run, we choose the epsilon as in this it is a kind of a linear. Uh, no, I think so. Yeah, it's a kind of a linear approach in which for every episode, it's calculated based on this, the max of 0.01 or 1 minus the episode divided by 5, 1 minus episode over 500, and then we run this. So that's the practical implementation trick that we use. The deep neural network that we have is two layers of dense, oh sorry, three layers of dense, uh, three dense layers with the ELU activations. Mm, and then this is used to solve the cardpole environment, a simple cardpole environment. And the number of observations are four. The number of the shape is four, and the number of outputs is two. Yeah, as this is the replay buffer that we have used, the maximum length of 2000 here. And each experience, this is a form of sample experience that we have. We have five values that the five elements that we return: the states, the actions, the rewards, the next states, and the dones. Dones are basically if they have reached a particular end state that they were trying to. And this is completely in NumPy. So if we take a look at the code, take it from the top. So uh, this let's build a DQN, give the state. It will estimate for one possible action the sum of discounted future rewards it can expect after it plays that action. Then this is the card pool, the input shapes, the para sequential layers that we made. Then this is the policy. with respect to the how the agent explores the environment, and we choose the random with the probability of epsilon. Mm, this is the prediction here, and the argmax we have taken with respect to the zeroth index, because the zeroth index has that uh, array of our q values that we need to take into account. Then this is the experience in the form of the agent's experience in the form of observation, action, rewards, next observation, and done. And we have used this TQ class. Yeah, this
My
is the
question,
yeah.
can you talk about the intuition of the replay buffer and what, I mean, he says instead of only relying on the latest, we'll store all experiences in the replay buffer, sample a random training batch from it. And why do we sample a batch? And then do we use the whole batch, or do we use one of the elements from the batch? And if you're using the whole batch, are we saying like whatever elements, meaning let's say the batch is made up of um, 10 elements, then are we making the agent take those 10 actions from 10 different states, or I'm kind of missing the big picture explanation rather than the nitty-gritty details of what we are trying to do when we create the replay buffer and when we then use it.
Cool. So yeah, we will get to it in this part of that problem with when we train this with respect to those batch size here. Instead of 10, we have here 32, the batch size that we are taking. And why we use 32 is because of the we can have I think so. Uh, I personally haven't tried the variations with respect to those batch sizes and how that affects the discount factor and the loss function here. But yeah, uh, uh, there was a famous post in 2018 that is also referenced here about having those training difficulties in for training our reinforcement learning based in environments. So uh, uh, here it is. Yep. Now let's talk about batch sizes and the replay buffers take into account come into account here. So what since what we're trying to do is getting the optimal policy with respect to the sharpness of the uh, uh, trajectory that we want. So think of it intuitively in a perspective of suppose we have multiple. Let me try to draw. There's two. And this is the prioritized experience replay research paper that was published in iClear in 2016, where they introduced this prioritized sweeping and this approach with respect to those samples that are taken, and we have to effectively narrow down the trajectory that we want, and uh, why this was taken into account with respect to those TD errors that I had shown earlier. And here they expanded on the number of uh, uh, this was the uh, probability of sampling a transition. This is with respect to those uh, the priority of a particular transition or the trajectory, as I've alluded to. And this is why our experience replay was taken into account. And they have two variants which they discussed in this research paper. One was the direct proportional prioritization, in which they use this formulation, uh, where epsilon is a small positive constant that prevents the edge case of a transitions not being revised once the error is zero. And the second variant was the indirect rank-based prioritizations. So these were the two variants that they used, and I think so they gave a elevation study with respect to both, and this was implemented for a double DQN, but yeah, we can implement this for a single uh, 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 vanilla Q learning, and then try that on to see the results. So this was kind of a how do I say it? Prioritize replay and uh, mm, those uh, uh, experience buffers that we had. So that was with respect to the inference. At the inference time, uh, how do we sample from that in a way to get mm, only those trajectories that we need to take into account to get nearest to the optimal. So I think so that explains it.
Mayan, can I ask a question?
Yeah.
Have you run this on your own with an Atari game or something? So trying to replicate what's in this paper, Huron's code, and just going step by step slowly to see how the model builds up from practical, step by step way.
Yep. This is it. So there, here, what we are trying to do is the same thing here. From a practical perspective, what they have done is they introduced a one hot encoding with the mask that we had. This mask helps in, how do I say it? This guy here. Uh, that mask out the Q values that we do not need. So this is a kind of oppose negative kind of approach as to what those actions that are actually not needed, and then we sum it across the axis accesses that to get the uh, properties, to get the values of those particular state action pairs that we need to get Q values for an experienced replay kind of a state action pair. So that's the practical way of implementing this, which Jeron has used here.
Okay.
Then we compute the loss and then we perform the final gradient step to apply those gradients in those 3 layers that we had. So that was with respect to theory, and this is with respect to the practical implementation of it. Then, yeah, these are the simple steps, the episodes that we had for the 600 episodes. Yeah, these are the steps that we had in a range of 200. So this is an episodic task, and yeah, rewards are appended, the best weights uh, here, and then best scores are taken with respect to that model dot weights and a step. If only that step is greater than the best score here. Yeah, this is done to uh, get those random, since we are choosing it randomly, sometimes or most of the times what happens is it will give us non-optimal uh, the parameters that are literally not optimal with respect to the algorithms that we uh, have to uh, cumulatively sum over. So that will be disregarded here. We ran it for 600 or 599 episodes with the steps of this. This is the epsilon that we had. 0.0 108. So that was the epsilon for the episodes that we used. And here we can see the sum of the reports with respect to how uh, what is the maximum here. So at at approximately 300, we have the performance that suddenly skyrocketed to 200. That's the cumulative sum of rewards that I talked about. And then it goes down back to zero, back to 25 approximately. Then it rises again. So that's the same uh, here in my uh, elevation studies. I reached 160 here. And then it had gone back to 15 or 20, and then 65, and then uh, 15 or 10, and then 100. So that's the catastrophic forgetting with respect to if we run it and we are trying to update it and those gradients are being lost. And so this experiences are correlated, and since the environments keep changing, since it is an episodic task, then these kind of problems are the practical problems are what we face, and we have to solve them. Mm, this is why this post was given in 2018. And this is the link that I have shared with respect to the practicalities of uh, reproduction in a particular uh, episodic task. because it's totally hard, and if you just try to tweak the parameters on the number of neurons, then the performance will never go above uh, what the research paper or the blog that was they was trying to convey. So the reproducibility part is low here. As I think so, they have given it in this paragraph. Yeah, and you can see from my experiments, they have reached here to 200, and I in my experiments was only able to reach above 160, so 165 or something like that. That is the problems that we face while actually trying to train it. Then any more queries? I think so. It's pretty much straightforward. If we take a look at this, training steps, the number of batches, we have seen this all before. The application of it, it's just yeah, a bit different here. And this is still simple because I needed to. We are already behind time. So behind in time. So now let's go to the deep Q learning variants. We take a look at the fixed Q value targets here. Here, what fixed target has, it's kind of a 2013 paper that I alluded to earlier. They had the online and the target model, and they were cloning it, setting the kind of weights that were similar, and were using uh, uh, those target models instead of the online model while computing the Q value. And then uh, they why they did this, because uh, uh, to solve the network stability problem. That's the practical problem that they solved. So there's a paper too here.
Hey, Mayank,
Yeah.
just excuse me for a sec. Let's try to end by 12 then, okay? Wherever we are,
Okay.
we should try to end at 12 so that people can count on being done after 2 hours when they come to this class. I think it's better that way.
Yeah, it is.
Okay, thanks.
Then okay, so let me try to go through this part of that double DQN. So let me go through fixed Q value and a double DQN, and we can take the rest afterwards. So yeah, as I was explaining with respect to the target and the online models that we have, and the problems that we faced, and how did we try to stabilize that training. So these are the hyperparameters that they used in their 2013 paper. uh, they use a tiny learning rate of this, updated every the target model was updated every 10,000 steps instead of 50 here. This the set weights that they have used here. I think so. They have the double DQN. We have yep. We are doing this here too. So every 50th step, we are copying the weights of the online model to the target model here. And as I alluded to, this was done to make it stable to solve the problem of divergence, oscillation, and freezing. Hmm. Also, there is an alternative implementation which they have kind of uh, commented out. You can uncomment it and use it with respect to the targets and the online weights at each uh, step. So you can use that too from an implementational point of view to see how your model is converging. Then we should also take a look at the prioritized experience replay, as I have shown here in the 2015 paper. This the prioritized experience replay and what they did here. And so why this was why this was used is in this paper they specifically sample those experiences that were important with respect to the task that we were trying to perform, and based on that particular bounds that we use that we reduce that variance with uh, those PD errors in mind, that this is what they have considered. And then those experiences that were recorded in the replay buffer, where the priority was very large, uh, was ensured that it was sampled at least once. So, this was done by this guy here. Yeah. And yeah. So the pay of zeta, where this zeta is a hyperparameter that controls how greatly that we want this important sampling to be, and this we adjusted from 0 to 1, and it obviously depends upon the uh, uh, variation between the uniform sampling and the full-blown importance sampling. And this is the hyper parameter. And there was one problem that they solved here with respect to that beta hyper parameter, which they defined is which they defined with respect to the important experiences that we had were needed to be sampled more often as compared to, and uh, uh, how can we control that? So they introduced the parameter beta here. Yeah, so that's it. And it is formulated as W is equals to N into the P to the uh, 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 power of a negative beta here, which we can use that. And yeah, I think so. Yeah, we are on time. Maybe we will take a look at dueling DQN later. And yeah, and it's kind of simple too. We have uh, So let's end it here, and we will take it through dueling DQN next time. Or if you guys have any more queries, yeah, you can ask me.
Thanks, Mayank. This was really great. Yeah, we're kind of within a stone's throw of the rest of it. Yeah. I was just going to mention to people who weren't here at the beginning that we have taken a poll that to gauge people's interest for a reinforcement learning study group once this hands-on machine learning group ends on April 4th. And so the reinforcement learning study group would start on April 10th and this time slot. And we got like almost 50 people interested. So you know, it looks like that group's going to go. I made an RL 2021 channel that people can join to keep abreast of whatever announcements that we'll be making in the next few weeks about the course.
Yep. Cool.
All right. Well, enjoy the rest of your day, everyone. And
Hey,
thanks a lot,
Joseph.
Mayank.
This one, Chan. Can I make a quick announcement?
Sure.
I posted a proposed group on the channel for building ML pipelines. And I'm sure many of you have seen it, and I've also posted it in the general channel. And I kind of mentioned it a couple weeks ago about this group and about this particular topic as well. I feel like this is a pretty important topic that's under discussed, under valued for sure, but it's actually highly demanded in the industry, and many of us are perhaps haven't spent enough time studying on that topic. So I want to bring that forward to see if more people are interested. And so far, haven't got too much attention. Maybe people are just not into it, which is fine. But I just want to kind of just bring that to everyone's attention. If you do like it, and if you do want to join it, please hit the thumbs up button or whatever reaction it is from that post. Then, in the end, I'll make a decision whether to start that group or not. And thank you, everyone.
Did you announce that on the general channel?
Yeah, as well. Yes.
Okay, great. And you're doing a poll to get interest?
Yeah. Well, not necessarily a poll, but people did, give a thumbs up. I've got 11 thumbs up from the general channel and 3 fires.
I see that. So I suggest that you actually spam the whole channel, because you're going to get almost 6,000 people who look at it if you do that. And with posting like you did, it's just going to be at random whether somebody checks the general channel. But if you spam the whole channel, I don't like to use that word, but I mean, you'll get 6,000 people to see your ad. And,
how do you do that?
You just go at channel.
I don't think we have that.
Oh, well,
I think you do have that. As you're the admin.
Well, you could write your ad, send it to me, and then I'll post it for you, and then make it into a poll, like I did for the reinforcement learning one.
Yeah, I saw that. Okay, I'll do that.
Yeah, and you're planning to go Wednesday nights?
Wednesday nights, yeah, and seems like that's a good time.
Yeah,
but
yeah.
Yeah.
Great. Okay, yeah, I'll wait for you to send me that, and then I'll post it for you.
All right, sounds good. Thank you.
Okay, have a good Sunday, everybody.
Have a good Sunday. Yep.
See you soon. Bye.
See you.
Thank you,
Bye.
man.
Take care.
Thanks, Mike.
Thank you, guys.